In this video, we're going to talk about a specific type of resistor configuration, but we call them bridge networks. And as you can see here, the standard configuration would have resistors here and here with one in between. A balanced bridge would actually be one in which we have no current through R5 and no voltage drop across R5, and we'll talk a little bit more about that later. But this is a standard bridge configuration. If we split this out so it didn't look like a triangle, this would be what it looks like, and this is also a bridge network. So we can use either mesh or nodal analysis to analyze our bridge networks. So we're going to use this circuit and we're going to analyze it first using mesh analysis, and then second using nodal analysis, and we're going to determine if this is a balanced bridge. So let's analyze this bridge network, and first we're going to use mesh analysis to do that. So we're looking at three different mesh currents here. We've got I1 right here, I2 right here, and I3 right here. So let's write our equations, and we're going to use the format approach to mesh analysis for these. So since we have three meshes, we're going to have an I1 column, an I2 column, an I3 column, and then our constant on the right hand side. Okay, so for our first equation, we are going to sum all of the resistances connected to that first mesh. So we've got a 3 ohm resistor, a 4 ohm resistor, a 2 ohm resistor, and we're going to multiply that by I1. Okay, so let me show you where that is, right here. So we've got the 3, the 4, and the 2. Now, we're going to look we're still in that first mesh, but we're going to look at anything that the first mesh has in common with the second, which is this 4 ohm resistor right here. So that's going to be minus 4I2. And then we're going to do the same thing with the third mesh, which would be this 2 ohm resistor that they have in common. So minus 2I3. And then the constant that goes on the right hand side, that's going to be our voltage source that's connected to that mesh. And in the clockwise direction, if it's going from minus to plus, which it is, that's a voltage rise. So that's going to be a positive 20. And there's our first equation. Okay, so there's one. So our second equation, we're gonna add everything that's connected to that second mesh. So R1, R2, and R5, and that'll be our I2 term. 4 plus 2 plus 5, I2. And then we're going to subtract in our I1 column whatever I2 and I1 have in common, which we saw before was that 4 ohm resistor. So minus 4 I1. And then we're going to subtract whatever I2 and I3 have in common, which happens to be this 5 ohm resistor right here. And then on the right hand side will be any voltage source connected to that second mesh, which there is none, so that would be 0. And then let's look at our third equation, which is our third mesh down here. And our I3 term now is going to be the sum of those resistances. So 2 plus 5 plus 1, I3. Where our I1 term is going to be whatever I3 and I1 have in common, which is the 2 ohm resistor, so minus 2 I1. And then our I2 term is going to be whatever I2 and I3 have in common, which is that 5 ohm resistor. That should be I2. And then on the right-hand side of the equation would be the constant coming from any voltage source connected to that mesh, and there is none. So now you can plug this straight into your calculator, and you get that I1 is equal to 4 amps. I2, the mesh current I2 is 2.67, and I3 is 2.67. Okay, so if I draw this in, where is I1? Well, I1 is all through here. It's in the outside of this mesh. So this is my 4 amps right there. It's not the current through R1 and through R3 because R1 has some current from the I2 branch, and R3 has some current from the I3 branch. So the 4 amps is not going to be the same there. So I2, where is I2? Okay, I2 is right here, and it's in the clockwise direction. All these came back positive, so they're all in that clockwise direction, and that's 2.67 amperes. And then I3 is also 2.67 amperes, and that's right here. So let's look at what that means. Right here at this junction, we have 2.67 amps coming in from that 2 ohm resistor, and we have 2.6 amps leaving through the 1 ohm resistor. So what does that mean for our branch right here? Well, if KCL is correct, there's no current there. Okay. So let's just kind of sit with this for a little bit, leave it the way it is, and we'll come back to that. And I'm going to make a note that I5 is 0 amps. And we'll come back to that in just a moment. Let's work the same problem again, this time with node voltages. Now to do that, I'm going to convert this voltage source here into a current source, and so we did that. It's 20 divided by 3 amps, and we put the 3 ohm resistor in parallel now with the source. So let's do our nodal analysis. We're going to use the format approach here. Again, we have our reference node here where V equals 0 volts, our V1 up here, our V2 here, and our V3 here. So we're going to have 3 columns, V1, V2, V3, and then our constant on the right hand side. So for the V1 equation, our V1 term would be the sum of the conductances connected to our V1 node, 1/3 plus 1/4 plus 1/2. Okay, let me show you where those are. The 1/3, the 1/4, and the 1/2 are all connected to V1. I hope you see that. And then we're going to subtract anything that V1 and V2 have in common, which looks like it's just this one right here. I don't see anything else connected to both V1 and V2. So minus 1/4 V2, and then we're going to subtract anything that V1 and V3 have in common, which is this 2 ohm resistor. And then on the right hand side will be our current sources. If they're coming into the node, they'll be positive, and if they're leaving, they'll be negative. So we have 20/3 amps coming in from that current source. Now for our V2 equation, let me get rid of V1 here. For our V2 equation, whoops, we're going to sum all the conductances connected to V2, so that would be these 3 resistors right here. So we've got 1/4 plus 1/5 plus 1/2 V2. Then we're going to subtract any conductances that V2 has in common with V1, which is just R1. So minus 1/4 V1. And then we're going to subtract any conductances that V2 has in common with V3, which is this resistor right here. So minus 1/5 V3. And then we're going to put any current sources entering or leaving V2 on the right hand side, and we don't have any, so that's going to be 0. Okay, so now we're ready for our V3 equation. So we're going to start with V3. So anything connected to the V3 node we're going to add down here, and that's going to be 1/2 plus 1/5 plus 1/1 V3. Okay, let me rewrite that. 1/2 plus 1/5 plus 1/1 V3. And then we're going to subtract anything that is connected from V3 to V1, which is that 2 ohm resistor. And then we're going to subtract anything that V3 is connected to V2 as well. So the 1/5. And then on the right hand side of the equation, any current sources connected to V3, which we have none, so that will be 0. Plug this straight into our calculator, and we should get V1 is 8 volts. V2 will be 2.67 volts. And V3 is 2.67 volts. So let me write in those voltages here. We've got 8 volts here, 2.67 volts here, 2.67 volts here. So notice something. If V2 equals V3, then what is the voltage drop across R5? Well, it would be V2 minus V3 or V3 minus V2, but that would just be 0. Okay, so remember what we found here was when we used mesh analysis, we saw that there's no current through that 5 ohm resistor. And when we used nodal analysis, we found that the voltage drop across that 5 ohm resistor is 0 as well. And this is what we call a balanced bridge. Okay, and it balanced bridge. Okay, so a balanced bridge is when I5 is 0 and V5 is 0. Okay, so there's no voltage drop across that middle branch, and there's no current through it either. And that happens when the ratio of R1 to R3 is equal to the ratio of R2 to R4, which, if you notice, R1 to R3, that's 4 ohms over 2 ohms, and R2 to R4 is 2 ohms to 1 ohm. Okay, so the ratio of both is 2, and that's what makes this a balanced bridge. So I just wanted to share that with you. We actually use that in several different circuits. For instance, you know, if you're trying to for instance, smoke alarms have this sort of configuration to try to determine when the voltage level is different across that R5, and so on. So that is our bridge. You can use mesh analysis or nodal analysis to solve for your bridge circuit.